All right, good morning, everybody. Thank you for the invitation, George, and to the organizing committee for organizing this special session. This is work I did as a postdoc at the University of Melbourne. Today is my second official day at Southampton. And Symon was one of my postdoc supervisors, and this is work I did in collaboration with this PhD student, Bo Jin. So the results I'm going to talk about today are currently under review, and thankfully a lot of people have given relevant introductory material, so I don't have to go through it again. I'm going to be looking at the cylinder wake, but I'm going to be looking at energy transfer mechanisms, and I'm going to try and then connect the dots between energy transfer and the other tools that we've heard from so far. So this is the DNS power spectrum of the cylinder wake. This is what the energy of the shedding mode looks like, and then we can compare this with resolvent analysis. And what's more interesting is what resolvent does not capture in comparison to what it captures. So it's missing peaks at all of these harmonics. The only peak it identifies is one at the shedding frequency, and this is related to the neutrally stable eigenvalue found by Berkeley. Another thing that resolvent doesn't get is its prediction of the first mode is actually not very good. And the reason I say that is because there is a huge amount of excess energy that occurs in the far wake. This is not unique to cylinder flow. This has been observed in jets and airfoils. And one of the things that we're going to try and explore is why do you not get the correct streamwise decay of this structure? So today, cylinder flow has been analyzed to death, but what I want to ask is what additional insight do we get from looking at energy transfer? So I'm just going to start with the 2D Reynolds-Orr equation. Everyone will be familiar with probably the 1D for turbulent flows. And we've written the Navier-Stokes equations in this form just so that we have L containing the linear terms that don't have pressure in them. And F is the nonlinear terms, which is sometimes called the nonlinear forcing and resolvent analysis. And so we're just going to take the inner product of the top equation with respect to U prime. And this is what is known as the 2D Reynolds-Orr equation that's discussed a bit in Symon and Henningsen. So everyone will recognize the top line here. This is just production that you get from the mean flow. And this is dissipation, of course, which is real and negative. But there are two additional flux terms here, which are line integrals. One has to do with mean advection out of the domain, and the last one has to do with the nonlinear terms advection leaving the domain. So what we'll show you in just a moment is that P and D are roughly balanced and that M and N are very small for this flow. The other thing we're going to look at is the energy balance for individual harmonics. So cylinder flow is beautifully sparse in frequency space. There are really only 3 active frequencies, which we're going to consider today. And it also satisfies an energy balance. So we now have the time derivative replaced by I omega. And we still have our nonlinear forcing here on this side, as well as the linear operator and the pressure. And when we turn the crank, we generate an equation which has the similar terms to the 2D Reynolds-Orr equation, but now the nonlinear term is no longer a line integral, it's a volume integral like the production, the dissipation. So this means that we're going to be looking at individual Fourier modes which are allowed to exchange energy with one another through this N term here. So just for the sake of simplicity, we're going to combine D and M into a single term, which we're going to call DE. This is just out of convenience because the dissipation is much larger than M. And we're going to look at how each harmonic satisfies this energy balance. And of course, when we add them all up, they also satisfy an energy balance. So if you haven't followed what I've talked about so far, hopefully this will illustrate what's going on a little bit more succinctly. So we've organized this by frequency. Omega-1 is just the shedding frequency. Omega-2 is the second harmonic. Omega-3 is the third harmonic. And what we see here is an energy balance for each frequency. It's not terribly exciting. We have a lot of energy production from the first mode, and this is counterbalanced on the left-hand side by dissipation in blue and nonlinear transfer in green. And then the second and third harmonic, they get very little production. In fact, most of their energy comes from the first harmonic, and this, of course, is balanced by dissipation. So what I'm showing you here is what the resolvent analysis predicts. So resolvent analysis does not give us the amplitude of the mode. The amplitude is set such that the resolvent mode has the same amount of kinetic energy as the DNS mode. So that's why they don't have the same production. It's because the modes are different shapes. If they were the same shape, they'd have the same production, but the resolvent structure is slightly different. And what is interesting is that production is completely counteracted by dissipation. There's absolutely no nonlinear transfer in here at all. Whereas for the second and third harmonics, you do get some nonlinear transfer, but you get no production. So that's going to be significant later on, because when we look at the aggregate energy balances now, so this is the same information I showed you in the previous slide. The only thing that's different is that we've organized by mechanism as opposed to frequency. We see that the balance between production and effective dissipation is met, and we see that the sum of nonlinear transfer over all the frequencies is met. Now, for resolvent analysis, this is not met. So the resolvent analysis specifies energy balance for each frequency, but not for each mechanism. So we see that the sum of n, for example, is not 0. Whoops, there's a positive component. And we see that p and d are not equal and opposite. So what does this look like spatially? This is a slightly intimidating slide. I would just like to focus your attention on the right-hand column, because this is the one that I think is interesting. So if we take a look at the first harmonic, there's a lot of energy removal that's taking place along the center line. And even though the sum of n for a point in space doesn't necessarily have to be 0, because it's the integral of n, what we can see is that a lot of this energy removal is then received by the second harmonic along the center line as well. And where the second harmonic loses energy is somewhat coincident with where the third harmonic gets energy. And so we'll look at mathematically more carefully how these frequencies are passing energy to each other in just a moment. Now, the next slide I'm going to show you are the resolvent predictions. And just to guide your eye, these two panels here are going to be roughly the same as each other. And the other 7 panels are going to look completely different. So Resolvent does a decent job predicting production and the dissipation maps, but it predicts no nonlinear transfer. And if we look at the second and the third harmonic, the Resolvent predicts a free stream mode, free stream structure. And the reason that the Resolvent struggles is because Resolvent is like a quasi-linear analysis. It gives you good productions of structures which take their energy from the mean flow. And as we saw from the energy balances previously, omega-2 and omega-3 don't get their energy from the mean flow, they get it from omega-1. So the Resolvent doesn't really have much hope in being able to predict what's taking place at these frequencies. So this is probably the most mathematically intense, but in my opinion, the most interesting part of the talk. This is explicitly looking at the nonlinear energy transfer, and we're going to do this through triadic interactions. So this is just a generic nonlinear transfer for a given frequency n. And as we know, the exponentials, when they're multiplying, their exponents add. So n will equal n minus m plus 1, m on this side. And what we're going to do is we're just going to consider this first term only for now. And we're going to dot this expression with ui minus n. So that's what I have here. So what this allows us to do actually is just by using integration by parts, what we can show is that the energy that m gives to n is equal and opposite to the energy that n gives to m. That's all this means. There is also a line integral term. This is energy flux out, but it's very small for this particular setup because the outlet domain is sufficiently far downstream. So this is another intimidating looking equation. The most important part is the left-hand side here. This is transfer from m as in mother to n as in nanny. Has to be equal to the transfer from nanny to mother. And another key thing to point out is that there are 2 terms in this equation. So you're allowed to have a cascade down, for example, and you're also allowed to have a cascade up. That's basically what this means, and we'll show you what that entails in just a moment. You'll also notice that there are 3 terms in each of these expressions. If we were to set m equal to 0, that would be the mean, so that would just be production. So you can kind of consider this term as a production produced by the mth frequency. And this is what we call the source mode, and the recipient is n. So m will give energy to n. And the third mode doesn't participate in the energy exchange, but it facilitates it. So this is called the advection mode. So this figure kind of neatly summarizes what's taking place in cylinder flow if you truncate after 3 harmonics. So there are 2 transfers between omegas 1 and 2. One is energy being removed from omega 1 and given to omega 2. But there's also a small amount of energy that omega 2 recycles back to omega 1. So that's why we have 2 terms in this expression here. So in this case, we can consider this is the source mode, this is the recipient mode, and these are the modes facilitating transfer. Now, we've truncated at 3 harmonics. Had we gone up to 4, we would have 2 terms, but we only have 1 term here. And this is the transfer between 2 and 3. And here 2 is the source mode, and it's giving to 3, and that's represented here by this green bar. So omega 2 is losing energy and omega 3 is gaining energy. And what's maybe a little bit counterintuitive is if we look at the final interaction, that's 3 and 1, the source mode is actually omega 3 and omega 1 receives energy. So this is kind of a feedback, so to speak, of the small scales back on the large scales of interest that's taking place in this flow. So in the remaining time I have, I just want to kind of relate this to our sort of alphabet soup of different reduced order modeling tools and sort of what has been already talked about by Stephen, Francois, and Yassine. And this is basically if we look at transfer between 0, which is the mean, and n, which is some harmonic, this is just a special case of the nonlinear transfer triads that we didn't look at before. So here we have the mean, this is the mean production. And what's useful is that if you only look at really production back and forth between the mean and the first harmonic, you can get the self-consistent framework that's already been discussed earlier. If we look at the Navier-Stokes equations in this term and we neglect the higher order interactions, this is how you recover the RZIF property. However, if you do include these interactions, what you can do is you can just remanipulate this equation and you can recover the resolvent. So here's that L minus I omega inverse, and that's what gives you the resolvent operator. And this is, in essence, what constitutes the nonlinear forcing. And these 2 terms are actually almost completely sufficient to reproduce the correct nonlinear forcing if you were to compute those quantities. And then last but not least, you can take a look at the higher order harmonics where linear analysis does not work. And if you force it with this expression, which is what Maliga did for a cavity and what we did for a cylinder, you would get a much better prediction of the second harmonic. So to conclude, hopefully I haven't gone too fast. This is kind of the picture I'd like you to remember in the future. This is where QL or resolvent analysis does a good job. This is with the first harmonic, gives you a good idea of what the production looks like. However, it doesn't model nonlinear transfer out of this structure. So as Stephen mentioned earlier, quasi-linear and resolvent are really only modeling interactions between the mean and fluctuations. So this would require a fluctuation interaction in order to produce. And it's quite important if you want to really recover a better structure, because without it, you predict no nonlinear transfer, and that's what results in these very long modes that have been seen by many other authors in the context of airfoils, jets, for example. And then the last thing I'd like to summarize with is just this little chart that kind of shows you how you can track these triads. So this was originally something that Smith came up with back in 1992, these 3-mode participation in these transfers. And here the source is the mean, giving you energy to the first harmonic. This is sort of a cascade down. And then you have other cascades and energy transfers taking place. So 1 and 2, there's a cascade down and up. The third harmonic does actually play a role in this. It's needed to facilitate this interaction. But you can also look at 2 to 3, which is sort of a cascade down as well, and then back up from 3 to 1. And then I'm happy to take any questions. So this is just another illustration of those energy transfer processes taking place in cylinder flow.